Thanks for having me here. My name is Ray. I'm a first year PhD student at the Technical University of Munich. And here I'm presenting our project. It's called FLAIR. The name is VLM with fine-grained language-informed image representations. And this project is done in collaboration with my collaborator, Sanwan, Lily, Zeynep, and Stephan. Also, like thanks Voxel 51 for hosting such a wonderful event. Okay, directly jump to the motivation is that why do we need to create this so-called fine-grained image representations? So here, like if you see this Starbucks image in the middle, here we basically just compute the cosine similarity between all these local image patches with this with the input text with the input text tokens. And here we show two text prompts where the first text prompt is describing the background and the second text prompt is describing the foreground, which is the Frappuccino. And so basically for all the existing large-scale pre-trained clip models, so basically this representation just doesn't change whenever you prompt anything, which is kind of fair because because nowadays like all these models they are basically just opt for this global level matching between your image representations and text representations. So we're also thinking that nowadays we can easily recaption images with MLLMs and we get this fine-grained captions that your for example your sub sentences might just represent like one just sub region of your image. So in that case, why not we just also get the image why not also get the partial image representation that only correspond to your language prompt? So that's the motivation. But to achieve this, basically we want this representation to be conditioned by the captions. So how do we achieve such a conditioning? Actually, we draw our inspiration from the attention pooling layer, and the attention pooling layer is nothing new, which is already inside the Siglib model. So basically, like for Clip, they basically just aligns this global level global image token with a global text token. And for a Siglib, what they add there is that they have one additional attention pooling layer in the end of the vision encoder. And you also have a learnable query, which is the VG here. And then you use the learnable query to pull your local image tokens and form the condition token in the end. And then you try to align your conditioned image token with your text token, global text token. And here we are thinking that, especially given the fact that if you already have a sentence which just describe one object in your image, so can we just directly use this sequence, this text as query, and we use it as a query to also just query the local image token so that the network can learn how to pull your image token adaptively. And in the end, we are trying to align this text conditioned image token with our global text tokens. So we're getting this language informed text representations. But meanwhile, we also empirically found that it's actually still beneficial to keep this learnable global image token, which is just the same as in Siglib or in Clip. Then we basically just keep this global level supervision between your global image token and your global text token. So we will keep saying that like we want to have fine-grained captions. So now the question is how do we obtain such diverse captions? So actually, like we did not create the dataset alone. Like so, basically, we just use the dataset from DreamLab, which is a work published in ECCV last year. And where they do is that they use multimodal large language models to recaption CC3 million, CC12 million, and YSCC15 million data sets. And so in that case, you can, for one image, you can get a long paragraph of sentences. So what we are actually doing here is that for each image, we basically randomly sample K sub-captions. And for each sub-caption, it can be the random combinations of and different sentences in this paragraph. So like these sentences can either be neighboring sentences or they can be just sentences in random position inside this paragraph. So In our main experiment, we mainly just sample 8 sub-caption per image, and like each sub-caption randomly combines up to 3 sentences. So having obtained such diverse captions, and the next question is how do we use it to create these representations? So actually now for one image, we can get k diverse ground truth captions. So here, if you see this orange color here, there are like 2 positive captions, which means that they are this ground truth caption sample from this image. And to avoid this information leakage problem, we also need to do a negative sampling, which means that we randomly sample one caption from every other sample in the same batch. So having obtained this both positives and negative captions, then we, for the image side, we basically just follows what clip does. Like, so basically each image is patchified and then encoded into a multiple local image tokens. And we also keep a global image token, which is a learnable token here. And so FLAIR mainly operates on 2 core losses. So the first loss is this test conditioned Sigmoid loss, where we use global text tokens as queries and local image tokens as keys and values. So for example, here you see that both the positive global text tokens and the negative text and global text tokens are passed as a query to the attention pooling layer. And what they are doing is that they're trying to basically just query the local image tokens so that this layer is supposed to adaptively select corresponding image tokens based on your text context. And so in that case, we're generating both positives and negatives text conditioned image tokens. And then we apply a sigmoid contrastive loss between this both positives and negatives text conditioned image tokens and this global text tokens. So basically this loss is to, let's say, pull like the both pull the both the positives text tokens away from the trying to push the positives tokens together and pull the negative tokens away, basically. So on top of that, we also have a multi-positive sigmoid loss, which is actually nothing new. It's just multi-positive version of siglib loss, where like we have a sigmoid loss between this learnable global image token and the global text tokens, basically. So basically, so now we have this this kind of text conditioned image embeddings. We try to show like the usage of such embeddings. So basically, we conduct a series of experiments, including zero-shot standard and fine-grained image text retrieval. We also have zero-shot image to text long text retrieval. We're also doing a zero-shot semantic segmentation, and of course, like everyone does, we also have a classification task. So basically, what we observe is that so like having trained a model like this, FLAIR can outperform this clip-like models trained on a billion scale data, like this, which is in the blue bracket here. And at the same time, when we evaluate the model on this zero-shot long image-to-text retrieval task, where one image is supposed to retrieve a long paragraph of text, we also observe that FLAIR, by pre-training on like 30 million images, it can outperform this long clip and lot clip, where they so basically they're basically dedicated trained for this task, and especially for the lot clip, like they also train themselves on 100 million images with long synthetic captions. So this shows that FLAIR basically can utilize such data more effectively to create this kind of fine-grained representations. We also did the zero-shot semantic segmentation task, where we observed that FLAIR can both outperform clip-like models trained on both billion scale web scale data, and also this clip-like models trained on the very same synthetic data under the very same configurations. In terms of classification, so actually we actually for the 3 million subset, we basically just we compare both FLAIR and also like clip and siglib, and we basically just train under the same configurations. Like here, we still see such a representation can be useful, but then we see this limitation of our representation is that like when we try to compare with OpenClip and MetaClip or ELIP, like these clip-like models, which is trained on billion scales of data, still like FLAIR cannot have a better performance than that. And intuitively, this makes sense because the intuition that we design FLAIR is that whenever we try to have a partial language prompt, we want the model just to focus on that part and just to produce an image representation, which only cares about that part. But classification is more of a global level task. It basically just challenge how the model can evaluate or just see the whole image and understand the whole image content. So yeah, intuitively, this also makes sense. So for me, like what's more interesting is to see whether we are like this attention pooling layer is really doing the job. So we further visualize the attention maps of the text condition attention pooling layer here with respect to a different text prompt. And so here we basically just manually show you that, okay, so for example, in the text prompt, like the red part is the stand for the main semantics. And the underlying part is basically this confounding phrases, which means that they doesn't represent the main semantics of the sentence. And if the model is good enough, if the model isn't good enough, they might be fooled by such a confounding phrases and just focus on this part. And here we show that by showing so red part stands for the regions with high attention scores. And we show that FLAIR can actually concentrate on the main semantics and ignoring the confounding phrases. So for example, if you look at the doc image here, so when the text is describing its pops are raised in the air and as if it's reaching out for something. So here the attention map is basically focused on only the raised paws instead of the other paws of the dog. So this can also marks, for example, there might be future applications or future research on whether we can do grounding or segmentation without any grounding labels or segmentation labels. So that can be a useful research in the future. We also visualize this fine-grained image text retrieval task. So here on top of the image, you see this top 5 retrieved caption when you're using the OpenClip models trained on 2 billion data. And so basically on the bottom part, like we show the top 5 retrieved result from FLAIR. So first, like you see that for OpenClip, they did retrieve some wrong text, but this is not what we're focusing on. For me, the interesting part is that if you look at the both sentence for these 2 models, you notice that for OpenClip, their top retrieved caption is some global level caption. It's like for example, it's like a view looking down at the metal cannon. But for FLAIR, the retrieved caption is more fine-grained. So which means that like FLAIR is focusing more on this small cannonballs are on 3 rows of wooden shelves. So this shows that we're indeed basically creating something that is more representation that is more fine-grained, and they have a different properties compared with a larger model. And yeah, this might be a good property, might not be a good property, but yeah, it's interesting to see the difference. So to summarize, we present FLAIR. It's basically a clip-like models featuring test-conditioned attention pooling layer. And we pre-trained FLAIR on 30 million images with our proposed diverse caption sampling strategies. And FLAIR can generate fine-grained language-informed image representations. We showcase such a power of representation is that it can outperform clip-like models trained on billion-scale data in 3 different levels of retrieval and segmentations, but there is still a gap in classification, especially when you try to compare with the models trained on crazy amount of data. And basically our code's models are available. And yeah, actually CVPR has passed. So, but feel free to have a chat here.